So, in today's lecture we will learn about what is known as Chernoff bounds. Okay. So, the question that we will address in this lecture is the following. Let us say we toss 1,00,000 coins and we will get some number of heads and some number of tails. What is the probability that the number of heads is greater than 75,000? Okay. So, we will look at the following problem. Toss n coins compute the probability that the number of heads is greater than, let us say, 3n by 4. Clearly, we expect, so if we denote by x the number of heads, then expectation of x is equal to n by 2. So, now here in this case the random variable takes a value much larger than its expectation. Okay. What is the probability of such a thing happening? So, this is a question of the following form: compute the probability that x is greater than a. We already have some tools to address these kind of questions. The first one, the Markov inequality. If we use Markov inequality, probability that x is greater than 3n by 4 will be less than or equal to expectation of x divided by 3n by 4. So, this is equal to n by 2 into 3n by 4. So, that is equal to 2 by 3. Okay. So, we can just conclude that the probability that the number of heads is significantly greater than n is going to be less than 2 by 3. If we use Chebyshev's inequality, so this is the probability that x minus expectation of x greater than a, this is going to be less than variance of x divided by a square. So, here expectation of x is n by 2. So, we have probability that n x minus n by 2 to be greater than n by 4. Okay. Whenever n is greater than 3n by 4, x minus n by 2 is greater than, the absolute value of that is going to be greater than n by 4. This happens with probability less than variance of x divided by n by 4 the whole square. Okay. Now, variance of this particular random variable is going to be n times p into 1 minus p, where p is the bias of the coin. So, that is going to be equal to n by 4. Therefore, here we will get this as n by 4 into n square by 16. So, this probability is going to be 4 by n, much better than 2 by 3. Okay. So, if you toss let us say 1,000,000 coins, the probability that the number of heads is greater than 0.75 million, probability that the number of heads is greater than 0.75 million, that is going to be something like 4 divided by 4 million. Okay. So, 1 in a million chance, whereas earlier bound would have told us 2 by 3. Okay. So, this is a Chebyshev's inequality is already a much better bound than Markov inequality. We will try to get a significantly better bound than both of these bounds, and that is what we will look at in this class. Okay. So, first, in order to understand what is Chernoff bounds, we will look at moment generating functions. Okay. So, let x be a random variable. So, clearly T x is also a random variable for any value of t, and e raised to T x are, so clearly T x and e raised to T x are random variables. So, we can compute the expectation of e raised to T x. So, moment generating function of this variable x is defined as the expectation of e raised to T x. So, look at this particular random variable, its expectation is going to be called the moment generating function. Note that the moment generating function is a function of a variable t. For each value of t, we will get a different random variable e raised to T x, and those random variables can have their own expectations. That expectation is called the, so that expectation is the value of mxt. So, this expression expectation of e raised to T x, that is going to be dependent on t, that function is called as the moment generating function. So, e raised to T x we can alternately write as expectation of 1 plus T x by 1 factorial plus t square x square by 2 factorial plus t cube x cube by 3 factorial, and so on. And by linearity of expectation, we can write this as expectation of 1 plus t times, t is a constant, expectation of x by 1 factorial plus t square into expectation of x square by 2 factorial plus so on. Okay. So, this is your mxt. So, you can verify that if you differentiate mxt with respect to t and evaluate this function at t equals 0, you will get expectation of x. Okay. So, the moment generating function has in itself the value of the expectation of the random variable embedded. Similarly, if you look at the second derivative, of the function mxt and evaluate it at t equals 0, you will get this to be equal to expectation of x square. In general, if you differentiate it n times, then you will and evaluate this at t equals 0, what you will get is the expectation of x raised to n. So, these expectations are what are called as the moments, and that is the reason why mxt is called as a moment generating function. So, now let us just look at the let us look at these moment generating functions more closely. If you have two random variables x and y, such that they are independent, then when you look at the random variable x plus y, so this will have a moment whenever it has a moment generating function. Okay. So, what will be the moment generating function of x plus y? Okay. So, this will be the moment generating function of x times the moment generating function of y. Okay. In other words, the moment generating function of x plus y is equal to mxt times myt when x and y are independent. Not too difficult to see. So, if you look at the random variable x plus y, its moment generating function is nothing but e raised to t times x plus y and the expectation of this. So, this is the moment generating function of x plus y. This is going to be equal to expectation of e raised to tx times e raised to ty. E raised to tx and e raised to ty are random variables in their own right, and those random variables are going to be independent random variables because x and y are independent. When you look at independent random variables and you want to compute the product of these random variables, the expectation of the product, that will be just the product of the expectation. So, this will be equal to expectation of e raised to tx times expectation of e raised to ty. So, this is because expectation of x y is equal to expectation of x times expectation of y when x and y are independent. Okay. So, but this quantity is nothing but moment generating function of x and this quantity is nothing but moment generating function of y. So, the moment generating function of x plus y is just the product of the individual moment generating functions. Now, let us look at the moment generating functions of indicator random variables, some particular examples. So, let us say x is a random variable which takes value 1 with probability say alpha and 0 with probability 1 minus alpha. What will be the expectation of x? What will be the moment generating function of? So, we want to calculate expectation of t e raised to tx. This is the moment generating function of x. Okay. So, this is equal to e raised to tx can take two values. E raised to tx is equal to either e raised to t, this happens with probability alpha, and this is when x is equal to 1, the value of e raised to tx is equal to e raised to t, and this is equal to e raised to 0, this with probability 1 minus alpha, and that happens when x is equal to 0. So, the two values that it can take are e raised to t and 1. So, the expectation of e raised to tx is alpha into e raised to t plus 1 minus alpha into 1. So, this can be written as 1 plus alpha e raised to t minus 1. Okay. So, this is clearly less than e raised to alpha t minus 1. Okay. Now, let us look more closely at the problem that we were interested in. You toss a coin many times. What is the probability that the number of heads is much larger than the expected value? Okay. So, in that the individual toss we will set up as indicator random variables, whether a head has appeared or not, and we will look at the sum of these. Okay. So, that is, and we will look at the moment generating function of these independent random variables. So, let us say that we have all these random variables x1, x2 up to xn, they are all random variables which take 0 or 1 value. Okay. So, this takes value let us say x1 takes the value 1 with probability mu 1, x2 takes the value 1 with probability mu 2 and xn takes the value n with probability mu n. So, clearly expectation of xi is equal to mu I, because this is 0 1 random variable, their expectation is same as the probability that they take the value 1. Okay. And if you look at this random variable, x is equal to x1 plus x2 plus xn, the moment generating function of x is going to be equal to, these are independent random variables. So, their moment generating function is just going to be a product of the individual moment generating functions. Okay. So, if mxit is the individual random variable, sorry, if xi is the individual random variable, mxit will refer to the moment generating function of the ith random variable, and this is equal to product I going from 1 to n. So, this will be less than or equal to e raised to, so here 1 plus alpha e raised to t minus 1 is less than e raised to alpha e raised to t minus 1. Okay. So, here this product is going to be less than e raised to alpha, instead of alpha you have mu I e raised to t minus 1. Okay. And this is nothing but e raised to, the product will translate into summation in the exponent, summation over I mu I e raised to t minus 1. Okay. And summation of the individual mu i's will be equal to the mean of the entire random variable. So, if you denote expectation of x to be mu, which will be equal to mu 1 plus mu 2 up to mu n, then this will be equal to e raised to mu e raised to t minus 1. Okay. So, we know that if we look at these random variables x1 to xn, which takes value 0 or 1 with probability mu I each, I mean mu 1, mu 2, mu I, then the moment generating function of the sum of these random variables is going to be less than or equal to e raised to mu e raised to t minus 1. These random variables have a name, they are called as Poisson trials. Okay. When all these random variables are identically distributed, this is also known as Bernoulli trials. Okay. So, in our experiment what we have is, we have these coin tosses, all of them having the same bias. So, we have identical coins being tossed. So, we have a sum of Bernoulli trials. So, our random variable is a sum of Bernoulli trials, and we know that in case of these kind of trials, the moment generating function has to be less than the quantity that we have derived here. Okay. So, we will use this fact later on, but right now let us try and see how we are going to put these things together and obtain what is known as the Chernoff bound. Okay. So, we were interested in questions of this kind, probability that x is greater than a. Okay. Now, this is same as, this probability is same as probability that e raised to t x is greater than e raised to t a, where t is greater than 0. Okay. So, we had an arbitrary random variable x, we have converted that into a positive valued random variable. Okay. This applies only when t is greater than 0, okay. And therefore, once we have converted this into a positive valued random variable, we can apply Markov inequality, and therefore, we will get this to be less than or equal to expectation of the random variable e raised to tx divided by a here being e raised to ta. Okay. Okay. Now, this statement is true for any value of t. In particular, we can choose that t which minimizes this expression. So, probability that x is greater than a is going to be less than minimum chosen over all t greater than 0 expectation of e raised to tx divided by e raised to ta. Note that the numerator and denominator are both functions of the variable t. Okay. So, you can try and optimize depending upon the random variable x and how its distribution is. E raised to tx, its expectation is going to have some functional form dependent on t, and so numerator and denominator both has t in them. You can try and figure out what is the best value of t, what is the smallest value that you can choose so as to minimize this expression, and even for that value this probability will be less than that. Okay. So, these kind of bounds are in general known as Chernoff bounds. Now, this is not a very useful form of Chernoff bound, but we will convert this into a nice form when x is, when we know something more about the distribution of x. We could also look at inequalities of the form, I mean we want to compute the probabilities that x is less than a particular a. Now, this is going to be equal to the probability that minus, or let us say we choose a negative number t. So, then this probability is going to be equal to the probability that tx is greater than ta. Here we will choose where t is less than 0, and this probability is going to be equal to the probability that e raised to tx is greater than or equal to ta. Now, e raised to tx so this is e raised to ta. Okay. Now, e raised to tx is going to be always a positive valued random variable, and therefore, we can say that this probability is less than or equal to expectation of e raised to tx by e raised to ta. Again we can minimize, so this is less than minimum over all values of t of this expression. Okay. So, these bounds are what is called as Chernoff bounds. It can apply both in the case where x is greater than a and x is less than a, and for any random variable x. Okay. So, now what we will do is we will convert Chernoff bound into a more useful form. Okay. So, we will try and obtain the Chernoff bound for these kind of events x greater than say 1 plus delta times mu. Okay. So, delta is a parameter that is given to us, and mu, let us imagine that it is the expectation of the random variable. We want to compute the probability that x is greater than 1 plus, so you expect it to be around mu, but what is the probability that it is greater than mu by an amount delta mu. Okay. So, and we will also look at probability that x is less than 1 minus delta mu. Okay. And together we will also look at, we will combine these two things together and compute the probability that x minus mu is greater than delta times mu. Okay. So, these will be specific cases of what are known as tail bounds. Okay. We will do this for the case where x is a sum of Bernoulli trials or even Poisson trials. Okay. So, we know that probability that x is greater than 1 plus delta mu is going to be less than expectation of e raised to tx divided by e raised to 1 plus delta times mu. Okay. t minimized over all values greater than or equal to 0. Now, if x is the sum of Poisson trials of n Poisson trials, then this quantity on the numerator, expectation of e raised to t x, we know is surely less than some quantity. We have derived this. So, this is the moment generating, this quantity here is the moment generating function of x, and we had shown that that is going to be less than e raised to mu e raised to t minus 1. So, we will use this result. So, we have this to be less than e raised to mu e raised to t minus 1 by e raised to 1 plus delta. Okay. So, this is going to be, this is equal to e raised to t minus 1 divided by e raised to 1 plus delta the whole raised to mu. Okay. So, what is the value of t that we will choose in order to make this quantity on the LHS, sorry, the RHS we need to make as small as possible. What is the value of t that we can choose? So, probability that x is greater than 1 plus delta times mu, we have shown that this is equal, this is less than or equal to e raised to t minus 1 divided by e raised to 1 plus delta the whole raised to, sorry, there is a t here, e raised to, the expectation is this quantity, and this probability that the probability that x is greater than 1 plus delta times mu is going to be less than this quantity. Okay, this is because this probability that x is greater than 1 plus delta times mu is going to be less than expectation of e raised to t x divided by e raised to t times 1 plus delta times mu. So, that is how the t comes in the denominator. Okay. So, this is our expression. We need to choose a value of t. Okay. So, any positive value of t would be fine. So, 1 t which can simplify things is choose t equals, so let us say we will choose e raised to t to be equal to 1 plus delta. Okay. So, this quantity e raised to t we will choose it to be 1 plus delta clearly. So, choose the t satisfying this expression. Okay, and clearly that t is going to be positive. If t is 0 you will get 1. So, little greater than 0 you will get 1 plus delta, as delta is some positive number. Okay. So, now this, so if we had chosen this as our value of t, we know that probability that x is greater than 1 plus delta times mu is going to be less than or equal to e raised to 1 plus delta minus 1 divided by 1 plus delta the whole raised to 1 plus delta the whole raised to mu, and this is equal to e raised to delta by 1 plus delta the whole raised to 1 plus delta the whole raised to the power mu. So, this is the probability that x is greater than 1 plus delta times mu. Now, let us look at this expression closely. In our scenario, we had x to be the sum of n IID random variables, and the expectation of x was n by 2. We wanted x to be greater than 3 n by 4, and we wanted to determine the probability of this, probability that x is greater than 3 n by 4. Now, in this case delta would be 1/2. So, probability, so we were interested in probability that x is greater than 1 plus 1/2 times the expectation n by 2, okay, and this by Chernoff bound is going to be less than or equal to e raised to delta here is half divided by 1.5 the whole raised to 1.5 the whole raised to mu, and mu is going to be n by 2. Okay. So, this is equal to, okay, so this is root e divided by 1.5 whole square, sorry 1.5 raised to 1.5. You can verify that this quantity is less than 1. Computation will tell you that this quantity is less than 1, and therefore, the probability of this happening is some quantity less than 1 the whole raised to n by 2. So, when n was something like 4 million, this is some quantity less than 1 the whole to the power 2 million. So, it is a much smaller number than whatever we had computed before, 1 by 1 million. Okay. Chebyshev bound gave us the probability to be less than 1 in 1 million, but here we are getting a probability some number which is less than 1 the whole raised to 2 million. Okay. Now, this number, is it really a small number, is it very close to 1? Okay. So, in some sense this formula is not really easy to work with, it does not really tell us how far is this away from 1. If this was, let us say, half, then we readily know. If this was less than half, we readily know that this is this gives a very good bound. Okay. So, let us try and convert this into a more workable form. Okay. So, we have this probability to be e raised to delta divided by 1 plus delta the whole raised to 1 plus delta. This is same as e raised to delta divided by e raised to log 1 plus delta times 1 plus delta, okay, and that we can write it as 1 by e raised to 1 plus delta log 1 plus delta minus delta. Okay. So, if we can show that the exponent here, let us call that as t, if t is greater than 0 for any value of delta, then we have some number which is strictly less than 1. So, this quantity, this entire quantity will be less than 1. Okay, so, this will be less than 1. Okay, so, we will try to show that. So, if you look at this expression 1 plus delta to log 1 plus delta and minus delta, you can plot the curves of these. So, this is a curve delta, okay, and 1 plus delta times log delta. If that curve lies strictly above this curve, then we know that 1 plus delta log 1 plus delta minus delta is going to be always positive. Okay. How do we show that? At 0, the function f1 and the function f2 are both 0, okay, because this is 1 plus 0 log 1 and this is 0. So, log 1 is 0. So, both of them are 0. So, f1 and f2 agree at 0, and if you look at the derivative of f2, that is, so f2 prime is 1, f1 prime is going to be 1 plus delta into 1 by 1 plus delta plus log 1 plus delta, that is going to be 1 plus log 1 plus delta. So, f1 is a function which grows faster than f2, okay, and they agree at 1. So, clearly this is going to lie above the, so this is a curve of f1, f2, and this is a curve of f1. Okay. So, this difference is always going to be positive. Okay. Since it is always going to be a positive number, we can write this as 1 by f delta, where f delta is going to be always greater than 1. Okay. So, this entire this tells us that this is going to be some f, let us say, so the probability of success, or the probability that x is less than 1 plus delta times mu is going to be always less than some, let us say, g delta raised to mu, and g delta is a number less than 1. Now, we will determine the form of g delta. So, we have this expression 1 by e raised to 1 plus delta log 1 plus delta minus delta. Okay. So, this we can write it as, so if you look at 1 plus delta into log 1 plus delta, if you just expand this is going to be 1 plus delta into log 1 plus delta, we can write it as delta by 1 minus delta square by 2 plus delta cube by 3 minus delta raised to 4 by 4, and so on. Okay. So, this, if we just multiply the terms, delta minus delta square by 2 plus delta cube by 3 minus delta raised to 4 by 4, and so on. When you multiply the delta, you will get plus delta square minus delta cube by 2 plus delta raised to 4 by 3, and so on. So, this is going to be equal to delta plus, this is going to be delta square into 1 by 1 minus 1 by 2 minus delta cube into 1 by 2 minus 1 by 3 plus delta raised to 4 into 1 by 3 minus 1 by 4, and so on. Okay. Clearly, this is going to be equal to delta plus delta square into 1 by 1 into 2 minus delta cube by 2 into 3 plus delta raised to 4 to 3 by 4, and so on. And what we were interested in is 1 plus delta into log 1 plus delta minus delta. So, this term goes away. So, this is going to be equal to delta square by 1 into 2 minus delta cube by 2 into 3 plus delta raised to 4 by 3 into 4 minus delta raised to 5 into 4 into 5, and so on. Okay. How large is this? This is the exponent of this term. Okay. So, if we call this as t, how large is t? Okay. We will show that t lies between delta square by 2 and delta square by 3. Time है ना? हाँ. So, we will show that t lies between delta square by 2 and delta cube by 3. Okay. So, t we know is equal to delta square by 2 by 1 into 2 minus delta cube by 2 into 3 plus delta raised to 4 by 3 into 4 minus delta raised to 5 by 4 into 5, and so on. Now, if you look at, if you combine any two terms, okay, if you look at delta raised to n, the first term is going to be a negative term, delta raised to n divided by n minus 1 into n. The next term is going to be a positive term, delta raised to n plus 1 divided by n into n plus 1. We can take what is common, delta raised to n divided by n, and then what is remaining is minus 1 by n minus 1 plus delta by n plus 1. The denominator is larger and the numerator is smaller, because delta we may assume is between 0 and 1. If delta is between 0 and 1, okay, when delta is between 0 and 1, these sum of terms taken 2 at a time is going to be a negative number, because this is smaller than this quantity, if you call it as b and this as a, minus a plus b. So, this, okay, if you call this entire thing as a, then a plus b is going to be less than 0, okay, because 1 is greater than delta, n minus 1 is smaller than n plus 1. So, the sum of all these terms, all these terms are going to be negative terms, and their sum is going to be negative. So, t is going to be at most delta square divided by 1 into 2. Now, if you take the summation in a slightly different way, that is, if you take these two together and the next two together and the next two together, you can see that each of these terms are going to be positive. Okay. So, t so therefore, t is going to be greater than delta square by 1 into 2 minus delta cube by 2 into 3, okay, and this is equal to delta square by 3 into 3 by 2 minus delta by 2. So, this is equal to delta square by 3 into 3 minus delta by 2. The maximum value that delta can take. So, this delta, the maximum value that it can take is 1, and even in that case this expression is going to be 1. So, this is no less than 1. So, the entire value of t will lie between, so the t should surely lie between delta square by 3 and delta raised to 2 by 2. Now, let us look at this expression slightly more carefully. We did this analysis for delta lying between 0 and 1, but 1 plus delta log 1, 1 plus delta minus delta, this is of course always positive. Since it is always positive, the value of this expression at 1 is going to be, I mean, whatever is the value of the expression at 1, that is going to be smaller than the values at all higher delta. Okay. So, if delta is greater than 1, greater than or equal to 1, then this expression p is going to be less than the value at 1, which is going to be 1 by e raised to 2 log 2 minus 1. Okay. We could have just simply written this as e raised to delta divided by 1 plus delta the whole raised to 1 plus delta. When delta equals 1, this is e divided by 2 square. So, that is e by 4. So, it is less than 3 by 4. Okay. So, when delta is greater than 1, we can readily substitute this by 3 by 4. So, 3 by 4 raised to mu, and when delta is less than 1, we have, so when delta is less than 1, we have the following theorem. So, for any delta between 0 and 1, probability that x is greater than 1 plus delta times mu is going to be less than e raised to minus delta square by 3 the whole raised to mu. Okay. So, this is e raised to minus mu delta square by 3. Okay. So, this is the form in which we are going to use Chernoff bound. When delta is greater than 1, of course, so if delta is greater than 1, then probability that x is greater than 1 plus delta times mu is less than 3 by 4 raised to mu. Okay. we can also derive a similar bound for any delta between 0 and 1, probability that x is less than 1 minus delta times mu. This we can show is less than or equal to e raised to minus delta square by 2 times mu. Now, here if you assume that x is a positive valued random variable, delta cannot, there is no sense in choosing a delta less than, let us say greater than 1. Okay, if delta is greater than 1, then 1 minus delta is going to be, let us say, a negative number. Okay. So, we can combine these two theorems and say probability that x minus mu is greater than mu times delta is going to be less than 2 times e raised to minus mu delta square by 3. Okay. We take the smaller of these quantities, okay, or smaller or larger. Okay. So, this probability is going to be the sum of these two probabilities, and mu delta square by 3 is going to be a smaller quantity than this. So, we can say that this probability is less than twice this, twice e raised to minus mu delta square by 3. Okay. So, when we try to prove this statement, okay, we just have to retrace the steps of the previous theorem, but instead of log 1 plus delta's expansion, we will have to work with log 1 minus delta's expansion, okay, and then everything else is the same, and we will get this as the bound. Okay, we will stop here for the time being. This concludes our discussion on Chernoff bounds.